We spent a session trying to understand superposition as was applied to interference in a Young's double slit experiment. Now, another important phenomena, which also actually is a case of superposition, which you're going to examine today, is what is referred to as diffraction. Obviously, you know, all of you from your very childhood, ever since you got acquainted and introduced to physics, you have learnt about what is referred to as rectilinear propagation of light. That is, light travels along a straight line, which essentially is the conventional theory in as far as propagation of light is concerned. Now, suppose there is an aperture AB. There is an aperture AB, and there is a source of light S. There is a source of light S, and there is a screen here. There is a screen here. Now you would expect light to travel along the straight line, along the straight line, along this, and very many paths between P and Q, right? This portion of the screen will be illuminated. This portion of the screen will be illuminated, right? Whereas you would see a shadow here and a shadow here, right? So there is a portion of illumination, there is a portion of shadow. Now, similarly, suppose there was an obstacle. Instead of an aperture, there was an obstacle. And there was a source of light S here, and there was a screen here. Then rays of light coming from the source would get onto the screen, and the portion above PQ, the portion above P or lower than Q, the portion above P or lower than Q, that's going to be illuminated. Whereas this is going to be the shadow region. This is going to be shadow region, as is suggested by rectilinear propagation of light. However, what was observed was, on decreasing the size of this aperture, as I decrease the size of this aperture, so that the size becomes comparable to the wavelength of light, of the same order of magnitude as wavelength of light. If the size of this aperture decreases and becomes comparable to the wavelength of light, or the size of this obstacle also decreases and becomes comparable to the wavelength of light, right? Then what really happens is light deviates from its straight line trajectory, and it encroaches the shadow region. It encroaches the shadow region. That means if I decrease AB, then for very small AB comparable to the wavelength of light, what really happens is there is an encroachment of light. There is an encroachment of light in the shadow region. I'm sorry, this is not the shadow region here. In this case, this is the shadow region. 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 Light encroaches in the shadow region. In this case, you would see light above P and you would see light below Q also, if the size of this aperture decreases. Encroachment of light in the geometrical shadow region, same thing here. If this obstacle becomes in size comparable to the wavelength of light, then the rays of light that come here, there is an encroachment of rays, there is an encroachment of light energy in the geometrical shadow region. In the geometrical shadow region. And this encroachment of light, subject to certain conditions, conditions as in, for the aperture, it becomes comparable to the wavelength of light. For the obstacle, this becomes comparable to the wavelength of light. Then this phenomena is called diffraction. This phenomena is called diffraction of light. So from its original trajectory, light would undergo an angular deviation. From its original trajectory, light would undergo an angular deviation. It flares out of its original trajectory. That means, let's say if it was supposed to be moving along this, and it flares out like this, then this angle at which it flares out, is called the angle of diffraction, And light in general would flare out or diffract at various angles theta from the same point. Now, this of course cannot be explained by the particle nature of light. It is primarily a consequence of the wave nature of light. It's primarily a consequence of wave nature of light. Now, all of us understand. Suppose there is a light beam headed in this direction, a parallel light beam headed in this direction, for example. This is the direction of the ray, right? Optical ray. Then a plane perpendicular to the direction of the optical ray is a wavefront. A wavefront essentially is the locus of points of the same phase, where all particles in that locus will be the same phase. That's a wavefront. So for a parallel beam, the wavefront are parallel planes, right? So this, for example, is a wavefront, When this wavefront encounters an aperture, this is an aperture, say, AB. Then the wavefront or the wave energy above A or below B dies out. As it encounters these obstacles above A and below B, it will die out. But the energy that is incident between A and B, what that does is, all particles between A and B get energized. All particles between A and B will get energized. And each particle in turn, as a consequence of wave theory, each particle in turn acts as a fresh source of light, acts as a fresh source of energy, acts as a fresh source of waves. Each of these particles would act as independent sources of waves. That means this particle, for example, would now act as an independent source, and it would emit what is referred to as secondary wavelets. This particle, for example, say A1, will emit secondary wavelets, right? It acts as a point source. This particle, for example, A2, this will also emit secondary wavelets. It will emit secondary wavelets. Each particle between A and B will emit secondary wavelets. These are wavefronts. These are spherical wavefronts. A point particle will emit spherical wavefronts. A point particle will emit spherical wavefronts. And A ray of light is always normal to a wavefront. A ray of light is always normal to a wavefront, right? So at A1, you know, one could conceive of a ray of light like this, which is normal to these concentric spheres. There could be a ray of light like this, which is also normal to these concentric spheres, which are spherical wavefronts. A ray of light could be like this. That means light flares in very many directions. It diffracts in very many directions, so to say, right? Realize that this was the original direction of traversal of light. Now it has flared out. It has diffracted. It has diffracted. Same with A2. There is a ray of light like this. Let me call this ray 1, for example. Let me call this ray 2. Let me call this ray 3, for example. You know, I've taken, let's say, 3 sample rays which are normal to the wavefronts, which are perpendicular to the wavefronts. So similarly for A2, A2 will also produce a ray, call it 1A, which will be parallel to 1, right? It will produce a ray which will be, say, call it 2A, which will be parallel to 2. It will also produce a ray which is parallel to 3, call it 3A. Yes or no? So which means, you know, all particles between A and B will produce rays that are parallel to 1, 1, 1A, and so on and so forth, right? Similarly, all particles between A and B will produce rays parallel to 2, 2A, etc. All particles between A and B will produce rays parallel to 3. Yes or no? So, which means the entire region can be broken down into sets of parallel rays 1, 2, 3, etc. and so on and so forth. This is what is going to transpire. So essentially, flaring out of rays, flaring out of waves, flaring out of rays. This is what transpires in diffraction. This is what transpires in diffraction. Now what we are going to study and examine is superposition of the diffracted beam. Superposition of the diffracted beam on a screen. I'm going to project this energy on a beam and examine the superposition on a screen. So essentially again, we are this time talking of a single slit, which has infinite number of secondary sources, In a Young's double slit experiment, we had 2 discrete sources, S1 and S2. This time we have infinite number of continuous sources between A and B, and we will look at their superposition on a screen. The fundamentals of superposition will not change. The basic ideas of superposition will not change. Only there is a cosmetic difference. Again, all of this falls within the jurisdiction of what is referred to as a single slit diffraction. Single slit diffraction. And again, in a single slit diffraction, there are 2 kinds. See, there is a source and there is a screen. This is a screen. One, what is called Fresnel's arrangement, Fresnel's diffraction. In this case, in a Fresnel's diffraction, the distance between the source and the screen is finite. In a Fresnel's arrangement, the distance between the source and the screen is finite. Is finite. That's one kind of arrangement. The other kind of arrangement is what is referred to as Fraunhofer's arrangement. In a Fraunhofer's arrangement, the distance between the source and the screen is infinite. The effective distance between the source and the screen is infinite. Infinite distance between the source and the screen. That's a Fraunhofer's arrangement. What we will examine is not Fresnel's arrangement. We will examine Fraunhofer's single slit diffraction. We'll examine Fraunhofer's single slit diffraction. We'll examine this pattern. All right. But so far so good. You understand what the basic premise is? How the various particles in an aperture, in a slit, they get energized and they act as secondary sources of light, each emitting its own wavelets, the secondary wavelets. And for each particle A1 and A2, there would be rays that will be parallel. So this one ray, let's say, has an angle of diffraction theta. Then this ray 1A also has an angle of diffraction theta. This ray 2 has an angle of diffraction, say theta prime. Then this ray 2A also has an angle of diffraction theta prime, and so on and so forth. Yes or no? Now, so we have an arrangement which looks like this. An accentuated view of the arrangement. This slit, however, is supposed to be very narrow, comparable to the wavelength of light. This is halfway between the slits, a central line, so to say. And there is going to be a screen that is going to be placed there. There is going to be a screen that is going to be placed there. One, what we do is, there is a source of light S. A single source of light S, which is a monochromatic source. Which is a monochromatic source emanating energy of wavelength lambda. Emanating energy of wavelength lambda. Monochromatic source. Monochromatic source of wavelength lambda. Monochromatic source of wavelength lambda. Now, what I want to do is, I essentially want this source to behave like a source at infinity. I place a lens here. I place a lens here whose focus is S. I place a lens here whose focus is S. All right. A lens whose focus is at S. Whose focus is at S. Which means if the rays of light are incident on this lens, if rays of light are incident on this lens, then after refraction, they run parallel to the lens. They run parallel to the lens. Right? Then, as far as the aperture is concerned, these rays are not coming from S, but they are coming from infinity. So it's as if the source, effective source, as far as the aperture is concerned, is pushed away to infinity, very far away from the source, because of the parallelism of the refracted rays. And this is the original direction of the rays. This is the original direction of the rays. Now, what I do is very, very close to this aperture, I place a converging lens. I place a converging lens. Thin converging lens. I place a thin converging lens. And at the focus of this converging lens, I place a screen. At the focus of this converging lens, I place a screen. There is a focus of this converging lens. At the focus of the converging lens, I place a screen. This is the focus of the converging lens. This is the focus of the converging lens. And I placed at the focus of the converging lens. This screen then, the entire thing lies in what is referred to as the focal plane of the lens. This entire thing is called the focal plane of the lens. So the screen is placed in the focal plane perpendicular to the principal axis. Perpendicular to the principal axis. This is the focus of the lens. This is the focus of the lens. All right. Now, very clearly, again, as the beam is incident on this aperture, it will produce infinite number of sources between A and B that will act as independent sources of energy, independent sources of waves, right? Thereby producing secondary wavelets. Which flare out and produce the phenomena of diffraction. And this flared out beam interferes or superimposes on the screen to produce a pattern. This flared out beam interferes on the screen and produces a certain pattern. This pattern will be referred to as the diffraction pattern. This pattern would be referred to as the diffraction pattern. We will have a preliminary examination of the diffraction pattern of the rays that interfere or superpose on the screen because of these infinite number of sources between A and B. The diffraction pattern would be examined. Yes or no? Now, this is the focus of the lens, and this is the focal plane. Very clearly, rays of light starting from A parallel to the principal axis, there will be rays parallel to the original direction also. You will have beam diffracted in all possible direction. Some part of the incident energy would also lie in the original direction. This is the original direction, right? This is the original direction, right? So there would be a beam. Part of the energy would also lie in the original direction because of these secondary sources of energy. It's going to flare out in very many directions, of which this is one, right? Now, so the beam or the energy which is parallel to the original direction would all converge to the focus of the lens? Would all converge to the focus of the lens? Yes or no? And realize that the energy arriving at F will all be in phase because all rays of light, this ray and this ray, would have traversed the same optical path in reaching F. This ray and this ray, for example, would have traversed the same optical path in reaching F. So pairwise, you can get rays that superimpose constructively at F because they would have traversed the same optical path on reaching F, and therefore they would be in phase with each other. And if they are in phase with each other, they would interfere constructively at F. Yes or no? For every ray like this, you can find a corresponding ray like this, which would have traversed the same optical path on its arrival at F. And therefore, this disturbance on reaching F through this pair would be in phase with each other and would produce constructive interference at F. Would produce constructive interference at F, and you get at F what is referred to as a central maximum. You get at F what is referred to as a central maximum. Yes or no? Now, having said this, so this we understand. There is a central maximum. There is also energy which diffracts from every particle here at an angle theta with respect to the original direction, right? There will be a beam parallel, but not parallel to the original direction, but diffracted at an angle theta with respect to the original direction, emanating from every single independent source between A and B. Yes or no? Let's examine that beam. Let's examine that beam or that energy, right? Now, let me just remove the clutter from here. So this we understand is a central maximum, and this would have very high intensity. Okay. Now let me look at this, of course, is the original direction. This, of course, is the original direction. Now, say there is a particle at A which diffracts the beam at an angle theta, flares out the beam at an angle theta. There is another particle here. There is again, it produces a ray diffracted at an angle theta parallel to this ray. There is a particle here that also produces a diffracted ray at an angle theta. At an angle theta. So this is a diffracted beam at an angle of diffraction theta. These are parallel rays. These are parallel rays, but parallel to each other, not parallel to the principal axis, not parallel to the principal axis of the lens, and not parallel to the original direction of the incident energy, right? So if there is on a lens, if there is a beam, parallel beam incident, then this beam will not get focused on the focus of the lens, but on the focal plane of the lens. This beam will also get focused on the focal plane of the lens. P would be a point on the focal plane of the lens. That means this beam, subsequent to refraction from the lens, would get focused on the screen which lies in the focal plane of the lens, which lies in the focal plane of the lens. Yes or no? So, again, you would expect the beam diffracted at an angle theta to get focused at some point P in the focal plane, to get focused at some point P in the focal plane of the lens. Yes or no? This is for a beam diffracted at an angle theta. Angle of diffraction for this beam is theta, right? We will examine, let's say, the path difference associated with angle of diffraction theta, for example. But so far so good, right? We will assume that AB, the width of the slit, AB, the width of the aperture, is small a and is comparable to the wavelength of light. Is comparable to the wavelength of light. Now, what I want you to take cognizance of is this is A, this is B, and say this was the screen. This was the screen, right? Very clearly, the beam diffracted at an angle theta. This is a beam diffracted at an angle theta, right? From B also diffracted at an angle theta. AB is small a. AB is small a, right? So the energy leaving A diffracted at an angle theta, the energy leaving B diffracted at an angle theta. There is a path difference between these two rays when they superpose on the screen. There is a path difference between these two directions, right? The path difference, like we saw, same mathematics. The path difference from A, I drop a perpendicular. From A, I drop a perpendicular onto this at say Q. Then BQ would be the path difference. BQ would be the path difference between these two, between this ray and this ray from A and B superimposing at P. Rays starting from A at an angle theta, rays starting from B at an angle theta, superimposing at a point P on the screen. The path difference is going to be given by BQ. Path difference is going to be given by BQ. So the path difference between the rays starting from A and starting from B diffracted at an angle theta is going to be given by BQ. Is going to be given by BQ. Now, this is theta. This is 90 minus theta very clearly, and like before, this is theta. Angle BAQ is theta. Angle BAQ is theta. Very clearly, BQ is A sin theta. BQ is A sin theta, as you can see. So the path difference is A sin theta, where A is the aperture width, right? And again, for computations, we look at small values of theta. That means points P not far away from the central line, not far away from the principal axis of the lens. So we will do our calculations on the premise of theta being small. On premise of theta being small, that means wherever required, I can replace sine theta by theta. Wherever required, I can replace sine theta by theta or tan theta, right? Again, this lens has a certain focal length and is placed very close to the aperture. That means this distance is really small. This distance is really small. And this is the focal length of the lens. And this practically is the same as its distance from the aperture. Distance from the aperture of the screen is practically the same as the focal length, let's say capital D of the lens. That means if I choose to call this as capital D, then for calculations I will look upon this also as capital D, the focal length of the lens, because the lens, I will assume, is placed very close to the aperture. Lens is placed very close to the aperture, right? So distance between the aperture and the screen is capital D, say. So one thing, I have an expression for the path difference of the beam diffracted at an angle theta between the upper extremity and the lower extremity of the aperture, which is A sin theta, where A is the width of the aperture. I understand this now. Now, if we understand this, can I just remove the clutter from here and get on with the thick of things? Right? So far, so good? Not an issue, right? Just to have clarity in the figure, I have just removed the unnecessary entities. Okay. A and B, there is AB is the aperture of length A. And like I said, this is a beam diffracted at an angle, say theta. Now, say a beam diffracted at an angle theta 1, say. The beam diffracted at an angle theta 1. All independent sources between A and B, all independent sources between A and B will produce rays diffracted at an angle theta 1, incident on the lens, eventually focusing at the same point on the lens which lies in the focal plane of the lens. Right? Let me look at this. Now, this is theta 1, this will be theta 1, right? And let me break AB into two equal parts, AC and CB. Let me break AB into two equal parts, AC and CB. AC and CB. Two equal parts, AC and CB. Each is A by 2. Each is A by 2. AC and CB both are equal to A by 2. There is incident energy diffracted at an angle theta 1. Incident energy at an angle theta 1 from C. From B also at an angle theta 1. Now, like I have discussed, if I drop a perpendicular AQ, right, this will be theta 1, then BQ would be the path difference. BQ, like I said, would be A sine theta. Now, so A sine theta 1 in this case. So now it becomes A sine theta 1. So now let me think of a certain theta equal to theta 1. Let me think of a theta equal to theta 1, a specific value of theta, call it theta 1, where A sine theta 1 becomes lambda. Let me think of a theta equal to theta 1. I can always select the angle of diffraction theta 1. I can't select the wavelength. I already have a fixed source S emanating waves of wavelength lambda, but I can on the screen select a point P. I can on the screen select a point P for which the angle of diffraction is theta 1, such that A sine theta 1 is lambda, the wavelength of the wave. I can select a theta 1 commensurate on the screen, angle of diffraction theta 1, such that A sine theta 1 is lambda. Now, that means this length BQ is lambda. Path difference between waves from A and waves from B is lambda. Now, I think of a diffracted beam at an angle theta 1 from the midpoint. From the midpoint, parallel to theta 1, parallel to theta 1 at an angle theta 1. This will also go to the same point P on the screen. Now, would you want to believe that if this length is lambda, this length will be lambda by 2? Yes or no? Similar triangles. This is halfway between them. So, if this length is lambda, then this length will be lambda by 2. Yes or no? Such is theta 1. Such is theta 1. Now, which clearly means that for such a theta 1, which clearly means that for such a theta 1, a vertical separation along the aperture by an amount theta 1, by an amount a by 2. This is a vertical separation by an amount a by 2 that results in a path difference lambda by 2. That results in a path difference lambda by 2. Yes or no? Which means between A and B, if I again select, let's say, some point P here between A and C, and a point Q here between B and C, and a point Q here between B and C, and examine the angle of diffraction theta 1 from P and Q, such that the separation between P and Q is a by 2, such that the separation between P and Q is a by 2, right? For every P between A and C, for every P between A and C, I can find a Q between C and B such that PQ is a by 2. So then if I have a P here and a Q here such that this is a by 2, then the path difference between P and Q, this will be theta 1. The path difference between P and Q, let me not call it Q, let me call this R, so that there is no confusion. I have used Q for this, so let me call it R. P and R. For every P between A and C, there exists a R between C and B such that PR is a by 2. Very clearly, then this will become a by 2 sine theta 1. This will become a by 2 sine theta 1. But a by 2 sine theta 1 is lambda by 2. Yes or no? Yes or no? Which means for every point between A and C, you can find a point R between B and C such that the path difference between these 2 points is lambda by 2. Yes or no? Path difference between these points is lambda by 2. If the path difference is lambda by 2, the phase difference is pi. Yes or no? Because lambda corresponds to 2 pi. So lambda by 2 will correspond to pi. Yes or no? That means P and R have a path difference lambda by 2. P and R have a path difference lambda by 2. So I have a phase difference pi, because lambda corresponds to 2 pi. Right? A path difference lambda corresponds to a phase difference 2 pi. So a path difference lambda by 2 corresponds to a phase difference pi. So rays starting from P and R diffracted at an angle theta 1, diffracted at an angle theta 1, where PR is a by 2, would have a phase difference pi, would have a phase difference pi, and therefore the rays from P and R would interfere destructively on the screen, would interfere destructively on the screen, yes or no? These rays would interfere destructively on the screen, and if they interfere destructively on the screen, what will they produce? They'll produce what is referred to as a secondary first minima. Secondary first minima. See, for every P I can find an R. So for every point between A and C, there is a corresponding point between C and B, which will produce diffracted rays at an angle theta 1, which will interfere destructively on the screen, which will interfere destructively on the screen, producing what is called the first secondary minima. First secondary minima. Yes or no? Right? That means when will that happen? That will happen for theta equal to theta 1. That means that will happen when theta becomes such that sine theta 1 is lambda, which is the wavelength of the wave, divided by A. Right? For theta equal to theta 1, such that sine theta 1 is lambda by A. For such thetas, you would find what is referred to as the first secondary minima. First secondary minima. See, if A sine theta 1 is lambda, then A by 2 sine theta 1 would be lambda by 2, isn't it? I have selected theta equal to theta 1 such that A sine theta 1 is lambda. So this will be a by 2 sine theta 1, isn't it? The part difference. So if a sine theta 1 is lambda, a by 2 sine theta 1 will be lambda by 2, isn't it? That's okay. So this sine theta 1 equal to lambda by a will give to us our first secondary minima. And since theta is small, theta 1 is small, sine theta 1 can be replaced by theta 1. That means the first secondary minima is produced for theta equal to theta 1 equal to lambda by a, where theta 1 is the departure from the original direction, angle of diffraction. Yes or no? I get my first secondary minima, first secondary minima on the screen. Yes or no? Clear now? Now, which means, can I remove the clutter from here? Which means, so theta 1 is defined for me, lambda by a. Which means on the screen, if I look at a point on the screen, this was the original direction, this is theta 1, this is the central maximum, that theta 1 equal to lambda by a, I'll be able to locate a point P on the screen where I see my first secondary minima. There is total destructive interference at P given for theta 1 equal to lambda by a. Now, from symmetry, if theta 1 equal to lambda by a in this direction gives a first secondary minima, you will also have for minus theta 1 a corresponding point P prime, which is also the first secondary minima. So there are first secondary minima symmetrically located about the central maximum, right? In this case, theta would be minus lambda by a. In this case, theta would be plus lambda by a, for example. Yes or no? So these would be symmetric points about the central maximum where you see the first secondary minima, right? Secondary minima of first order, we can say secondary minima of first order. Now, this PP prime is called the linear width of the central maximum, is called the linear width of the central maximum. Linear width of central maximum. And 2 theta 1, which is this angle is 2 theta 1, this angle is 2 theta 1, this 2 theta 1 is called the angular width of the secondary maximum. Of the secondary, of the central maximum. Of the central maximum. 2 theta 1 means 2 lambda by a. And what is PP prime? Hey, suppose this distance is d between the aperture and the screen. This distance is d, right? Then very clearly this approximately is going to be r theta kind of a thing. So d into lambda by a. So this is going to be lambda d by a. Do you all understand why so? This is almost going to be the arc length. Arc is r, which is d into theta. D into theta. D into lambda by a. This is also going to be d into lambda by a. lambda d by a? Yes or no? Right? So this whole thing, which is the linear width of the central maximum, linear width of the central maximum, which is 2 lambda d by a, is the linear width of the central maximum. Linear width of the central maximum. Essentially what happens then is, so far so good, right? So so there is a first order secondary minima above the central maximum, and there is a first order secondary minima below the central maximum, right? Symmetrically located. So on the screen, this was central maximum, where you would have seen, let's say, high intensity. Let me say this designates the high intensity. And at P and P prime, you see the first order secondary minima. First order secondary minima. Intensity varies from maximum at central maximum to 0 at first secondary minima. Maximum at central maximum and 0 at first order secondary minima. First order secondary minima. So this is a region around the central maximum. This is the region around the secondary maximum, where you see greatest intensity, where you see greatest intensity of the beam, right? Now, if you have registered this, I will move. So at the central maximum, you see high. So this is only a geometric representation. High intensity at the central maximum, it reduces to 0 at first order secondary minima. First order secondary minima, P and P prime. And this region around the central maximum is the linear width of the secondary maximum. And 2 theta 1 would be the angular width of the secondary maximum. Point C. This is 2 theta 1. Which we've already obtained. Right? Now, let me proceed. Let me now look at a case a diffracted beam at an angle theta 2, say a diffracted beam at an angle theta 2. So between A and B, endpoints of this aperture this is theta 2, this is theta 2. So all points between A and B would produce rays parallel to theta 2. That means at an angle theta 2 with the original direction, right? Now I select theta 2 in a special manner. I select a point P on the screen with theta 2 subscribing to a certain condition, right? I'm talking of a certain point P for which theta is theta 2. Interference at such a point P on the screen for which theta is theta 2. And realize that every point, every particle between A and B would produce secondary wavelets at an angle theta 2 with respect to the original direction. Now, what theta 2 am I going to select? This time I'm going to select theta 2 in a manner that the path difference between the rays from A and from B, such would be my theta 2, which is like A sine theta 2, such that, right, this AB is A, this AB is A, this angle like before is theta 2, such that A sine theta 2 is 2 lambda, is 2 lambda. Let's examine such points. A sine theta 2 is 2 lambda, such is how I select my theta 2. Obviously, theta 2 is more than theta 1. As you can readily see, theta 2 is roughly twice theta 1 in fact for small theta. Right? So further away from the central maximum, this time further away from a central maximum, I select points P for which theta is theta 2 given by this. Now what happens to such a point P for which the angle of diffraction is theta 2 given by A sine theta 2 is twice the wavelength of the incident energy. Right? Now this time what I do is the region between A and B, I earlier divided it into 2 equal parts. Now I divide it into 4 equal parts. I select a point P1, P2, P3. I select points P1, P2, P3, dividing AB into 4 equal parts. Dividing AB into 4 equal parts, A by 4, A by 4, A by 4, A by 4 and A by 4. And from these points, again, you know, at an angle theta 2 parallel to the direction angle parallel to these beams from A and B. These rays from A and B. Now, the path difference, so A and P1 are at a vertical separation of A by 4, for example. Right? P1 and P2, A by 4. P2 and P3, A by 4. P3 and B is also A by 4. Same vertical separation. Same vertical separation. Do you realize that this length grows from 0 to 2 lambda over A, right? In four equal divisions, right? If this is 2 lambda, that means each time it must have increased by lambda by 2. Yes or no? Because first time it increased from 0 to some value and then increased by the same value from here to here, increased by the same value from here to here. So in 4 parts it increased by 2 lambda. This was 2 lambda. Right? So each time it must have increased by lambda by 2. That means this path difference must have been lambda by 2. This length must have been lambda by 2. This length must have been lambda. This length must have been 3 lambda by 2. And this length if it was 2 lambda. Similar triangles, basic proportionality theorem. Right? If this is 2 lambda, and these are 4 equal parts, then this must be lambda by 2, this must be lambda, this must be 3 lambda by 2, and this must be 2 lambda. Yes or no? Right? Between A and B. Do you all understand this? This is 2 lambda. This is from P1. This length is lambda by 2. This is lambda. This is 3 lambda by 2. Yes or no? That means now, please understand this. From A to P1, what's the vertical separation? A by 4. That means every time you move vertically a length A by 4, the phase difference that results is lambda by 2. Yes or no? Every time you move a distance a by 4 along the aperture, the corresponding path difference that results is lambda by 2. If you move another a by 4, another path difference, lambda by 2 results. If you move another a by 4, another path difference, lambda by 2 results. You move another a by 4, another path difference, lambda by 2 results. Yes or no? Such is my theta 2, such is my theta 2. This part difference is 2 lambda this time. This, like I said, will be lambda by 2. This length will be lambda. This length would be 3 lambda by 2 and so on and so forth. Right? Now, the important thing is, so 4 equal parts, 4 equal regions, 4 equal regions. The rule of the game then is, every vertical descent of a by 4 results in a path difference lambda by 2. Another vertical descent of a by 4 results in a path difference lambda by 2. That means phase difference pi. That means phase difference pi. Which means now I can select a point P here between A and P1 and a point R here such that PR is a by 4, such that PR is a by 4, then the path difference between P and R would be lambda by 2. Path difference between P and R is going to be lambda by 2. That means rays starting from P and rays starting from R, when they interfere on the screen, let me call it P prime and R prime, because again, I've called P as a point on the screen to avoid confusion. So if P prime R prime is a by 4, then the path difference between P prime and R prime would be lambda by 2. Phase difference would be pi, and therefore these waves would interfere destructively on the screen. Yes or no? That means all points between A and P1 would find a corresponding point between P1 and P2 where there would be destructive interference, at the point P on the screen, given by A sine theta 2 equal to 2 lambda. Such is theta 2. A sine theta 2 equal to 2 lambda. If such are the points, then for every point between A and P1, there is going to be a point between P1 and P2 which will interfere destructively on the screen, giving me 0 intensity on the screen. Similarly, so all points between A and P1 would get cancelled by corresponding points between P1 and P2 on the screen, right? Similarly, all points, for every point between P2 and P3, I can find a corresponding point between P3 and PB which will interfere destructively on the screen, as long as this separation is a by 4. A vertical movement of a by 4 will result in a path difference lambda by 2, phase difference pi, and destructive interference on the screen. That means this will get cancelled with this will get cancelled with this. There will be complete cancellation occurring at the point P on the screen given by this. There would therefore be a minimum on the screen. For theta equal to theta 2, given by that, there would be another minimum on the screen, and this minimum is called the secondary minimum. This theta 2 given by sine theta 2 equal to 2 lambda by A. That means replacing sine theta 2 by theta 2 approximately, that is theta 2 equal to 2 lambda by A is secondary minimum. Similarly, I could have chosen A sine theta 3 equal to 3 lambda, broken it into 6 parts, and I would have again got complete cancellation. A sine theta 4 equal to 4 lambda, breaking it down into 8 equal parts, neighboring parts cancelling each other and giving me destructive interference. That means, what thetas will give me destructive interference on the screen? Theta is given by A sine theta equal to an integral multiple of lambda. N equal to 1 will give me theta equal to theta 1, first secondary minimum. N equal to 2 will give me theta equal to theta 2, second secondary minimum. N equal to 3 will give me theta equal to theta 3, third secondary minimum. And for theta equal to theta n, this will give me the nth secondary minimum. Nth secondary minimum. Right? That means this is nth secondary minimum. Which is replacing sine theta n by approximately theta n. I get theta n approximately as n lambda by A. N equal to 1 will give me first secondary minimum. N equal to 2 will give me second secondary minimum, and so on and so forth. Where theta n's are the various angles of diffraction for which the first secondary minimum, second secondary minimum, third secondary minimum, and so on and so forth would be obtained. Right? Now you understand that? Now, so far so good, right? Can I remove the clutter from here? Now again, A and B. Let me look at angle of diffraction beta equal to beta 1. Let me look at angle of diffraction beta equal to beta 1 from various sources between infinite sources between A and B. Right? So, all particles between A and B, you can find a corresponding ray getting diffracted at an angle beta 1. Now what I do is, again AB like I said is small a, the width of the aperture. Right? And Q is the foot of the perpendicular from A onto this diffracted ray. This will, like before, be beta 1. This path difference, again like before, is going to be A sine beta 1. Right? Now, I select beta 1 in a very special manner. I select beta 1 in a manner, a beta 1 on the screen in a manner, say where A sine beta 1 is 3 lambda by 2. Okay. Let me select theta equal to beta 1 on the screen, such that A sine beta 1 is 3 lambda by 2. That's a fixed point on the screen. For theta equal to beta 1. Now, the region between A and B, I divide into 3 equal parts. This time, for minimas, I divided the region between A and B into an even number of parts. 2, 4, 6, 8, etc. Now the region between A and B, I divide into an odd number of equal parts. Say 3 equal parts this time. Say 3 equal parts. Alright. So 1 P equal to P1 parallel to this beam. P equal to P2 parallel to this beam. Alright. 3 equal parts, AP1, P1, P2, P2B. Each will be A by 3. Each will be A by 3. A by 3. Alright. Now, A sine beta 1, which is this is 3 lambda by 2. Right? This length is 3 lambda by 2. And these are 3 equal parts. So it has, this length has changed from 0 to 3 lambda by 2 in 3 equal stages. Then again from proportionality theorem, do you realize this will be lambda by 2, this will be lambda, and this will be 3 lambda by 2. Yes or no? That means this length is lambda by 2, this length. This length is lambda and this length is 3 lambda by 2. Yes or no? Do you all understand this? Now, the rule of the game then is this time. Every time you move vertically down by an amount A by 3, path difference changes by an amount lambda by 2. If you move down by an amount A by 3, path difference changes by an amount lambda by 2. If you move down by an amount A by 3 vertically along the aperture, path difference changes by an amount lambda by 2. Yes or no? Right? Which means now, can I select a point M1 between A and P1 and a point M2 between P1 and P2, such that if M1, M2 is A by 3, the path difference between the rays from M1 and rays from M2 would be lambda by 2. Path difference lambda by 2 means phase difference pi. That means destructive interference. That means for every M1 between A and P1, there is going to be an M2 between P1 and P2 where the path difference is lambda by 2. Phase difference is pi, and there is going to be destructive interference. Yes or no? Right? See, did I tell you that if you move down by an amount A by 3, the path difference will change by an amount lambda by 2? That means phase difference will change by an amount pi. Right? So if I can find an M1 here, then I move A by 3, any M1 between A and P1 I select. I move down by an amount A by 3. Then the path difference will be lambda by 2. Phase difference will be pi and rays from an M1. And there is a unique corresponding point M2 where there would be complete cancellation because of path difference lambda by 2, phase difference pi. That means the ray energy from A to P1 would get completely annulled by the energy from P1 to P2. Because for every M1 there would be a unique M2 where there would be perfect cancellation. There would be destructive interference as long as the vertical separation is A by 3. Yes or no? Path difference will be lambda by 2 and there is going to be complete cancellation. Yes or no? So AP1 would get cancelled with P1, P2. So then P2B does not get cancelled. 1/3 of the energy, right? In this region there is 1/3 of the energy is now available on the screen. 1/3 of the energy is now available on the screen. Yes or no? Of the 3 regions, 2 regions have participated in destructive interference, and this then will cause illumination on the screen. Right? This then will cause illumination on the screen. What point on the screen? point on the screen for which theta is beta 1 given by A sine beta 1 equal to 3 lambda by 2. Such will be the point P on the screen. Again, beta 1 is small. Beta 1 is small, right? So, beta 1 is approximately 3 lambda by 2A. This will be this point beta 1, or this point beta 1 is called the first secondary maximum. First secondary maximum on the screen. First secondary maximum on the screen. And 1/3 of the light is available on the screen in the first secondary maximum. First secondary maximum. Similarly, what I could have done is, can I remove all of this? Now, I select theta equal to beta 2, theta equal to beta 2. I select theta equal to beta 2. Such that the path difference between rays from A to B1, which is A sine beta 2, right? BQ, which is A sine beta 2. This time I select as 5 lambda by 2. This time I select as 5 lambda by 2. Right. Now I divide the region between A and B into 5 equal parts. P3, P4. These are 5 equal parts in which I have divided the region between A and B. Evidently, again, do you realize that in 5 stages, this grows from 0 to 5 lambda by 2? Right? That means each time it grows by lambda by 2. That means this length is lambda by 2. This length is going to be 2 lambda by 2. That is lambda. This length is going to be 3 lambda by 2. This length is going to be 2 lambda. And this length is going to be 3 lambda by 2. I'm sorry, 5 lambda by 2. 5 lambda by 2. That means each time you move by an amount A by 5 along the aperture, the path difference changes by lambda by 2. Phase difference changes by pi. And it's going to cause destructive interference. That means for every point between A and P1, say M1, you can find a corresponding point M2. You can find a corresponding point M2 between P1 and P2. As long as M1 and M2 is A by 5, the path difference is going to be lambda by 2, phase difference is going to be pi, and energy diffracted at an angle beta 2 from M1 and M2 will interfere destructively on the screen. Yes or no? That means AP1 would get completely cancelled by P1, P2. P2, P3 would get completely cancelled by P3, P4. What remains? P4B. P4B, it illuminates, but 1/5 of the energy. So now this still is a maximum, but the intensity at this maximum is less than the intensity at the previous maximum. At the previous maximum, only 1/3 of the energy was reaching. And this time 1/5 of the energy is reaching for illumination of that point P on the screen. So this point is the second secondary maximum. If A sine beta 2 is 5 lambda by 2, then this beta 2 gives me the second secondary maximum. And the intensity at the second secondary maximum is less than the intensity at the first secondary maximum. Why? Because lesser amount of energy is reaching the second secondary maximum compared to the first secondary maximum. And this beta 2 is going to be given by 5 lambda by 2a. On the premise that beta 2 is small, sine beta 2 could be replaced by beta 2. And in a very general sense, next I could have said, well, 7 lambda by 2, break it into 7 equal parts, there will be one unattended part, 1/7 of the energy will reach, that will give me the third secondary maximum, which will be less intense than the second secondary maximum, and so on and so forth. Yes or no? So in a very general sense, A sine theta equal to an odd multiple of lambda by 2 will give me secondary maximum. Such thetas will give me secondary maximums. Of unequal intensities, of unequal intensity. If you plug in n equal to 1, you get the first secondary maximum. If you plug in n equal to 2, you get the second secondary maximum, less intense than the first secondary maximum, and so on and so forth. With decreasing intensities, you get the maximas. Central maximum, of course, is more intense than the first, second, third central maximums. Yes or no? Right? And so, and A sine theta equal to n lambda will give me secondary minimas. Minimas, n equal to 1 plus minus 1 plus minus 2 etc. will give me secondary minimas of various orders. Right? The intensity therefore no issues, right? The intensity graph versus theta on the screen. The intensity graph versus the theta on the screen. This is theta equal to 0, which is the central maximum, and it has highest value of intensity. It has highest value of intensity, say I naught. And then the intensity goes this way. At theta equal to lambda by A, first secondary minimum, at lambda at theta equal to 2 lambda by A, second secondary minimum, this is 3 lambda by A, first secondary maximum, first secondary maximum, first secondary maximum. Three lambda by A, third secondary minimum. Halfway between these two, you get 5 lambda by 2a, 5 lambda by 2a, second secondary maximum whose intensity is less than the first secondary maximum, and so on and so forth. This will be the graph. And so on and so forth. Is that okay? And similarly on this side, symmetric graph on this side. Minus lambda by A, minus 2 lambda by A. Symmetric graph on this side about the intensity axis. Right? This obviously is the linear width of the central maximum. 2 lambda by A is the linear width of the secondary maximum. Is the angular width of the secondary. 2 theta. It is 2 theta. 2 lambda by A is the angular width of the central maximum. 2 lambda by A is the angular width of the secondary maximum. 2 theta. Theta and minus theta. 2 theta. Angular width of the central maximum. Do you all understand single slit diffraction Fraunhofer? No confusion?